If you're studying rational functions, a key feature you need to understand is the idea of a horizontal asymptote. If you're watching this video, I'm assuming you have some basic understanding of rational functions. If not, feel free to check out the linked video and jump back in here once you're up to speed. Alright, so let's talk about asymptotes. For the sake of simplicity, let's divide asymptotes into two groups, vertical and horizontal. Vertical asymptotes result from restrictions on x. They're off-limits lines that the function is unable to cross. For rational functions, this happens when the denominator is equal to 0. This is best illustrated with an example like this. We'll say this function here, 1 over x plus 2 times x minus 2. You can see that there are two possible x values that would make the denominator 0. X equals minus 2 and x equals 2. From here, you can imagine what the graph of this function would look like. These asymptotes at negative 2 and 2 force my function to behave in a way that the graph would look something like this. Now, I'm not going to go into detail as to where this graph comes from. I will have other videos on vertical asymptotes that will explain this. But it's kind of interesting to see that this function does not touch the line y equals 0. But how would I know that this happens at y equals 0? How do I know that there's a horizontal line here that this function will never cross? That's the purpose of this video, to look at these horizontal asymptotes, understand where they come from, and predict what the graph might look like as a result. Horizontal asymptotes can be found by asking yourself, what y value does the function approach as x approaches infinity? So if I take my x values and I make them very, very big, what happens to my function? What value does it approach? That's the question we're going to answer in this video today. It is worth mentioning that there is a third type of asymptote called oblique or slant asymptotes. These are closely related to horizontal asymptotes, but they're kind of like the weird, crazy ant in that they're related to horizontal asymptotes, but also quite different. So we're not going to cover that in this video. I will link another video to this that will walk you through how to understand and sketch oblique asymptotes in detail. So horizontal asymptotes result from two cases. The first one is when the degree on the bottom is greater than the degree on the top. So for example, if we look at this function here, the degree on x in the denominator is 1, and on top it doesn't appear that we have an x term visible, but remember there is sort of an x to the power of 0 here. Remember, x to the power of 0 is just 1, and so you can see here the degree on top is actually 0. So I do have a higher degree on the bottom than on the top. So what we want to do is look at our definition of horizontal asymptotes, which remember was what happens to the function as the x values get bigger and bigger, and I want to analyze what happens to this particular function. So in this case, as x approaches infinity, you should see the bottom get larger much faster than the top because the degree is higher on the bottom. You can demonstrate this by subbing in a few really big numbers. If we start with a number like, for instance, 100, I sub in 100, I subtract 4, 1 over 96 is 0.0104, rounded to 4 decimal places. Now 100 is a big number, but I'm going to sub in an even bigger number like 10,000. When I sub in 10,000, I subtract 4, 1 over 9,996, 0.0001. So even closer to 0 than when I subbed in 100 and got 0.0104. So you can see that as x gets bigger and bigger and bigger, or as x goes off to infinity, my y values are approaching 0. So it's safe to say that I will have a horizontal asymptote at y equals 0. Now graphically, here's what this function looks like. I just graphed this quickly on Desmos. You can see as my x values get bigger and bigger, 2, 4, 6, 8, and so on and so on and so on, this function is decreasing, slowly approaching the value of y equals 0. The same thing will happen if I sub in really big negative numbers. This thing's going to approach 0. So that's where the horizontal asymptote comes from in this situation where the degree on the bottom is bigger than the degree on top. Let's look at the second case. In this case, the degree on the bottom is equal to the degree on the top. So you can see this function here. I have 2x plus 1 on top. I have x plus 2 on the bottom. The degree on each of these x's is 1. So I have the same degree on the top as on the bottom. And I can approach this the same way by investigating what happens to the function as the x values get larger and larger. So if I use the same x values as before, I'll use 100, I'll sub in 100, I get 1.9706. 100 is a big number, but 10,000 is an even bigger number. If I sub in 10,000, I end up getting 1.9997. And you can see that as I sub in bigger and bigger numbers, I'm approaching the value of 2. So I can conclude that the horizontal asymptote for this function will be at y equals 2. Now, interestingly enough, if you go back to the original function and you sort of ignore the +1 and the +2 here, you can see that the ratio of the coefficients on x is 2, or 2 over 1. That is not a coincidence. As it turns out, this is a nice shortcut for finding horizontal asymptotes when the degree on top is the same as the degree on the bottom. And so if you think about the definition of a horizontal asymptote, as x approaches infinity, how much does adding 1 or adding 2 really matter? And the answer is not at all. So the resulting graph would look something like this. On this graph, you can see my horizontal line at y equals 2. The function approaches that line as x gets really, really big in the positive direction and in the negative direction. So that's the second case, where the degree on the bottom is equal to the degree on top. Okay, so the last thing I want to show you is a pretty bizarre thing that can happen with rational functions. This seems kind of counterintuitive, which is crossing a horizontal asymptote. And I know what you're thinking.
Grr, but you said we can never cross a horizontal asymptote.
Now, before you spam me in the comments section with negative feedback, let's revisit both of our definitions for vertical and horizontal asymptotes. Vertical asymptotes are not possible to cross because they involve restrictions on x, like dividing by 0. That is not possible. It never will be possible with our current understanding of mathematics. Horizontal asymptotes happen as x gets bigger and bigger or goes off to infinity. So you can not cross a vertical asymptote, but you can cross horizontal asymptotes at times. So in this case, if I sub in a really big number like 100, for instance, you can see that this thing is approaching 0, and you can see that on the graph of this function. But if I sub in a number very close to 0, so locally, for instance, like -1, if I sub in -1 into this function, I get 0. And that's what you're seeing right here on the graph. So just remember the definition for horizontal asymptotes. These are y values that a function approaches as x approaches infinity, not close to 0. I know, math is weird. Speaking of weird, how is our weird distant aunt, the oblique asymptote, doing? She is, of course, waiting for her own video tutorial, which you can find linked here. Thanks for watching. If this helped you in any way, feel free to like this video and subscribe for more mathematical chaos.